now we want to revisit a topic we saw in both Calculus 1 and Calculus 2, which is finding limits. In particular, right now we're interested in finite limits, so limits at particular values. So we have a few definitions we need to learn. A closed region is a region that includes the boundary. So you can see that when I drew it, I'm drawing a solid boundary line. And a boundary point is any point that's on that boundary line, and an interior point is any point that's inside the region, in the interior of the region, if you will. An open region has a dotted boundary line, right? Because it's everything except for the boundary itself, right? And so interior points are still points inside the region. A boundary point is a point that would be on that boundary, on that dotted line around the region. Now, if we want to evaluate a limit, interior points are easy. Interior points, we just substitute the values, and you're done. Because an interior point is never going to give you grief, right? It's not a problematic region. The problematic regions are the boundaries. And a boundary point means you're going to have to use some algebra and pre-calculus to find the limit. Now, what are some potential algebra and pre-calculus things we might have to use? Oop. There, I had to fix that. Okay, so some potentials would be factoring. We might need to rationalize. We might need to multiply by a common denominator or something like that. I'll just say multiply by a value. Just leave it at that. And there may be others. Everything you ever learned in algebra class. All right, so let's do an example here. Now this example is going to be pretty easy. Part A is, that is, because this piece is going to be in the interior. But first we have to prove it. So let's start by finding the domain. So we need the domain, and it does say to sketch the domain right here. And we need it anyway because we need to know whether our value is an interior point or a boundary point. Okay, well, the thing about algebra class is that we learned that you cannot divide by 0. Okay, so that means that my denominator cannot be 0. So y minus 4 cannot be 0, which means y cannot be 4. Now we know what y equals 4 looks like because we all made it through Algebra 1. Y equals 4 is a horizontal line. So there's the line y is not equal to 4. And, or if you will, y equals to 4, but it's dotted. And the domain is all the other points in the xy plane except that. Now it didn't ask us to actually write down the domain, so we'll just leave it at that. Suffice to say that we've sketched it. But it's all the real points, or all the points in r squared except for y equals 4. Okay, so now we have to look at 2, 5. Over 2 up 5 is right here. It's an interior point. All right, so we've identified the point being approached, and it's an interior point, so we can just say that right there. And then we're going to find the limit. Right, so I'm just making sure I've sketched my domain, I've identified my point as an interior point, and I'm going to find the limit. Well, the limit's really easy. Since it's an interior point, all we have to do is substitute. So we just take 2 and put it in for x, and we take 5 and put it in for y. That gets us 4 plus 3 over 1, which is 7. There we go. We have our domain sketched. We have our interior point labeled, and labeled that it is an interior point, and we have our limit found. Now, of course, interior points, very easy. Let's practice some that are not interior points, shall we? Of course, first thing we're going to have to do is prove that it's not an interior point. We start by sketching the domain. All right. So now for the domain, we know that we cannot divide by 0. And there's nothing else really problematic in here. There's no square roots or logarithms, things like that. Right? Okay, so we know that the denominator cannot be 0, which would mean y cannot be 2x. Now y equals 2x is a diagonal line that looks like that. Right? So we know that we can have everything to the left of that line and everything to the right of that line, but not the line itself. Right? So that's our domain. Okay, now we need to find 3, 6. Over 3 up 6 is a boundary point, because 3 times 2 is 6. So that's a boundary point. So we're going to have to use pre-calculus. Now, what pre-calculus are we going to use? Well, let's look at the problem. If I look at this and I'm thinking into my bag of pre-calculus tricks, I'm thinking that I'm going to factor, because that numerator is factorable. So I'm going to take xy goes to 3, 6. Now I'm going to rewrite my numerator with parentheses, because I'm going to factor. Right? That's our pre-calculus trick. All right, now if this is going to work, then 2x minus y is going to be one of these factors. That way things will be nice. So if I was going to make 2x squared, that must mean x is in the front position, because 2x times x would be 2x squared. And I want to make minus 4 in the back, and I have a minus y right here, so I'm going to try a plus 4y right here. Now we can double check with FOIL that this works. First would be 2x squared, outers would be 8xy, inners would be minus xy, which makes 7xy, and then minus 4y squared. So this works. Yay. All right, so then this is the limit as xy goes to 3, 6 of, well, when these go away, it ends up just being x plus 4y. Right? There's no denominator anymore. So I didn't really need the division line, I suppose, because it ends up being over 1, if you will. Right? Because these two go away. Right? They divide to 1. Oh, okay. So now I can direct substitute. I couldn't before. I mean, if I tried, if you put 3 and 6 in here, you're going to end up with 0 over 0, which is an indeterminate form. And there's no L'Hopital's rule to save us. L'Hopital's rule was for functions in one variable, not functions in 2 variables. So we don't have any options here, right? We cannot just direct substitute. Until this point, now we can. So now we say, okay, 3 plus 4 times 6 is 3 plus 24, which is 27. So there's the limit. Here's the fact that it's a boundary point. There's the domain. But one other thing to think about before we leave this behind is, what's this showing us? So if I'm going to call this, z equals f of xy, just bear with me here. That function is equivalent-ish, if you will, to x plus 4y, which is a plane with a diagonal line missing. Right, the diagonal line of y equals 2x missing. And the point we found, 3, 6, 27, is on that missing line. Let's go look at it in Maple. So you can see here I've got the function graphed as it was originally given to me. And you can see it actually turns into a plane because z equals x plus 4y is a plane, right, when it cancels. And we're left with this plane with this diagonal stripe kind of missing out of it. Right? Wonderful. All right, let's do one more. So we have this lovely piece over here. Now, this is going to give us a couple problems with domain. All right, so there are things that we can't do from algebra. We cannot take the square root of a negative. So the domain is actually going to have a couple issues. We know that the numerator is going to tell us that x plus y has to be greater than or equal to 0, because I can't take the square root of a negative number. I can take the square root of 0, that's fine, but I can't take the square root of a negative. So that means y has to be greater than or equal to negative x, period. So that's part number one. Now part number two comes from the denominator, which is that x plus y minus 9 cannot be equal to 0, right? Because we can't divide by 0. So square roots have to be positive. Logarithms also have to be positive as well. And denominators have to be not 0. Right? These are classic things we learned in algebra. So this would mean x plus y cannot be 9. Okay, so that's a diagonal line, right? Let's draw this. Okay, so y equals negative x is a solid line. And I know I'm to the right of that line because I have to be greater. Y has to be greater than negative x, which is over here on the right side. But I also know x plus y cannot be equal to 9. So I'm not going to draw this to scale, but there you have it. So this is y equals negative x. This is y, or x plus y equals 9, if you will. Okay, so I can have everything to the right of this, but not that diagonal line. And it cannot go to the left because over here on the left would have caused a square root of a negative, and that's bad. All right, so there's my sketch of my domain, which was one of the requirements for the problem. Next, they want 0.45, which I'm sorry to tell you is right here. It's a boundary point. And you can tell it because 4 plus 5 makes 9. So that's how you know. There are lots of boundary points, but that's one of them. So I'm going to circle that. So that's one of the pieces they asked for. 4, 5, sketch the domain and tell me whether 4, 5 is a boundary point, and it is. So that means we have to use algebra. Okay, so what algebra are we going to use this time? Well, actually, I'm going to do it right off the bat. I'm going to do something called rationalizing. Rationalizing is when you multiply by the conjugate. So it's the same as the radical. This is a binomial with a radical, and you multiply by the same binomial, but you switch the sign. Right? Those are called conjugates. You should have learned about them a long time ago in Algebra 1 or Algebra 2. All right, so then we multiply. And of course, when we're multiplying here, this is a binomial times a binomial. So I'm actually going to FOIL out the numerator. So this is the limit as xy goes to 4, 5 of x plus y, right? Because first would be square root of x plus y times the square root of x plus y, which is just x plus y. Take away 9. And the denominator, I'm just going to write it like it is. X plus y, take away 9, square root of x plus y plus 3. I don't need to FOIL that out because it's going to go away, right? Because the whole reason for multiplying by the conjugate is it makes this part disappear. And I'm left with finding the limit, and yes, you have to keep writing the limit notation until you do your substitution, which we're not there yet. What's left when we divide is 1, right? We're really dividing. When a number is divided by itself, it makes 1. Now we can substitute, right? So now we can say, okay, that's 1 over the square root of 4 plus 5 plus 3, which is 1 over the square root of 9 plus 3. That's the square root of 9 is 3. So this is 1 over 3 plus 3, which is 1 over 6. All right, so there's the limit. So I've made my domain. I found that it was a boundary point, and I found my limit. And we did something called rationalize. That's what we were doing. All right, so now what does this mean? Well, let me call this z equals f of xy again. If I say that that's a function, the graph of that function would be the same as the graph of 1 over the square root of xy plus 3, but it has this diagonal line missing. All right, so the graph of our original function is the same as the graph of this function, but it's going to have that diagonal line of x plus y equals 9 missing. And technically the whole graph is to the right of y equals negative x. There won't be anything over here. And that point that we found, 4, 5, 1, 6, is on that missing line. Let's look at it in Maple. At least I'm thinking I graphed it. There it is. Okay, so here it is. You can see oops, let me kind of swing it around. The whole graph is above the diagonal line, right? You can see it's not going anywhere. Now, it's not really showing the diagonal line that's missing, and that's okay. That sometimes happens with these graphs because they're really hard to show every piece of it. But at the very least, I can tell that the whole thing is above that y equals negative x line, like that. Sometimes Maple just doesn't do a good job of showing the wobbly bits, the lines that are missing or whatever. That happens. It's not the end of the world, but nevertheless, we can still see the other parts. And we'll just have to trust in our own mathematical skills for why the other line must also not be there, even if Maple's not graphing it well for us.